Hey everybody. So week 4 office hours. Here's the questions we're going to be looking at so far. We've got the Lewis structures activity looking at N2O2. Then we've got mastery question 6, problem 15, which is looking at how we get empirical formulas and molecular formulas from line drawings. And then functional groups looking particularly at aspirin and testosterone. And I put these in the order that I think is best for solving these. One kind of leads to the next, leads to the next. One thing I'll point out is that for all of these, if you haven't watched the 5th video, I do a kind of quick review. I do physical chemistry, so I don't do a lot of organic chemistry, and I'm not the best at knowing the right way to do things for organic chemistry. So I made a quick video of like the simple things I do to get it so my colleagues that do organic chemistry don't make fun of me when I try to draw a structure. And let's go ahead. We're going to do N2O2 in 2 different ways. We're going to do it the quick way, using the kind of rules that I set out in that video. And then we're also going to do it in the more formal way that Dr. Neff went through in her 2 videos. So the quick way is to realize nitrogen wants 3 bonds. Oxygen wants 2 bonds. And we like to put the lower electronegativity thing in the middle. So in this case, it's going to be nitrogen. In those cases where we have carbon compounds, carbon's usually in the middle. Hydrogen, of course, is never in the middle because it cannot bond to anything besides itself. So I'm going to start with just making a chain, keeping the oxygens away from each other. And then I'm just going to try to follow these rules of nitrogen wants 3 bonds, oxygen wants 2 bonds. 2 bonds, 2 bonds. Nitrogen has 3, nitrogen has 3. Fill out the lone pairs. Done. Now, this is after me having years of practice getting good at recognizing the patterns. So let's talk about how we can go through this a little bit more of a formal way. So then we just have to put this into LabPal and get it to agree. But these 3 bonds, 1 lone pair, and these 2 bonds, 2 lone pair, these pieces are already designed to guarantee the lowest possible formal charge in the structure. So these are going to have formal charges of 0. They're also designed so they already have 8 electrons around them. 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So if we use these simple pieces, we'll always make a good structure. Whether it's actually something that exists or not is a different question. Let's do this the formal way and see if we get the same idea. So we're going to do this in a couple steps. Step 1, count valence. Step 2, you're going to essentially make a guess skeleton, a skeleton structure. You're going to propose like a guess structure. We usually call it a skeleton structure. I'm just going to call it proposed structure. And then the final check is checking formal charge to make sure it's the best possible structure. So you'll notice this is going to take a lot more time than the simple like check it thing that we did earlier. But this is going to work, this process is going to work for things that even don't follow our typical situations. So when we get into things that don't follow the hypervalent compounds, sulfur and phosphorus, when they don't follow the octet rule, this works for those. If we're looking at excited states or free radicals or anything that's weird, this process in blue will work, whereas this process of recognizing the patterns only works like 85% of the time. So let's go ahead and do that for N2O2. Count of electrons, of course. Periodic table handy. Nitrogen has 1, 2, 3, 4, 5 valence electrons. So I'm going to get 2x5 from nitrogen. Oxygen has 6 electrons, so I'm going to get 2x6 from oxygen. That's going to be 10 and 12. So I'm going to have 22 electrons. That's going to be my count of electrons that I have to distribute around my structure. Then proposing the structure, we're going to use the same idea we had before. Less electronegative elements go in the middle. More electronegative elements go around the outside. So we end up with the same kind of base structure. That's the proposed kind of skeleton structure. And now we want to go through and fill our octet. So you'll notice at this point, I've only used 2, 4, 6 electrons. So I'll get a little -6 there. And that will leave me with 16 electrons left to distribute. So I have to put 16 electrons around this structure, trying to make sure that everything ends up with 8 electrons around it. And it's really hard not to just put the right answer right away. So let's do a common mistake that people make. So if you looked at this, you'd say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 electrons. Ta-da! If you just put a triple bond in the middle and lone pairs around, this gives you a fine structure. You've got your octets full. Nitrogen has 8 electrons. Each oxygen has 8 electrons. But when we go to do this formal charge check, we'll find that the formal charge on this is not the best. So, and then we'll have to fix the structure. So let's go ahead. We'll do the formal charge on oxygen is going to be equal to the number of valence electrons. That's going to be the 6 valence electrons, minus the lone pair electrons, which is -6, minus half of the bonding electrons, which is 1 bond counts as 2 electrons. This oxygen is going to have a formal charge of -1. This oxygen is also going to have a formal charge of -1 because it's the same thing. We can then go ahead and do our formal charge on nitrogen. We'll have the 5 electrons, valence electrons, minus 0 lone pairs, minus 1/2 of the bonding electrons, 2, 4, 6, 8. That's going to be -4. That's going to give us +1. And the thing we need to know about formal charge, let me do a quick check with the people in office hours. You can use if you click on participants, you can click yes or no. And I'm going to ask you a yes or no question. I feel like I understand formal charge. Oh, okay. Seems like most people understand formal charge. So we'll just move on from there. We can see this and we can say, oh, there's got to be a way to get a better formal charge. And if we go back and think about those common pieces, instead of having a double bond there, so after we realize that we have too much formal charge, we can go through and try to propose a new structure. And instead of having a double bond there, I put my double bonds on the outside, bring those electrons in, and then we can do a formal charge on this one, and that's going to be the 0, 0, 0, 0 formal charge. And the best structure is going to be the one that has a formal charge as close to 0 as possible, with as many zeros as possible across the structure. So that's going to be our N2O2 structure in the short version of it and the kind of longer version of it. Any questions on that? Did that make sense? I think, was that your question, Ashley? Can't remember who asked it.
No, that was mine.
Oh, okay.
Yes, that made sense. Thank you.
Cool. Were you doing the triple bond in the middle?
I think I was dispersing it a bit. It was kind of a mess, but
Okay.
it makes sense now.
Well, another thing that people will commonly do is they'll do a double bond, single bond with the lone pairs to fill it out. And that actually also distributes the right number of electrons. But again, when you go to your formal charge check, to see how well everything is splitting its electrons across it, you find out that you have a better way you can write it. Formal charge is kind of this really fascinating thing to me, because in my mind, when I think about why does a molecule have a certain number of bonds and a certain number of lone pairs, I'm really thinking about all of these ideas like valence shell, electronegativity, electron affinity, relative electronegativity, and formal charge just kind of gives us this quick mathematical check that takes all of those ideas into account. So it's pretty neat. So that was Lewis structure. Let's go ahead and take a look at mastery question. Let's take a look at mastery question 6, set 6, problem 15. And I'll go ahead and read this one real quick, if I can find it. So this has a lot of text to it. This week we explore interpreting molecular structures, blah, blah, blah. Talks about how we get to the line drawings, talks about benzene. Enter your formula using the following order, CHNO. You'll notice that order is not just because we felt like it. It's in order of electronegativity. Not quite. Carbon and hydrogen have approximately the same electronegativity, but carbon and hydrogen about the same. Nitrogen and oxygen, more electronegative. They go further off to the side. So we're going to enter our structures, and it says, oh, you can skip D and F, but we're actually going to do D. Now, if I remember correctly, Kimberly, this was your question. Did you do any of them? Did you do A or B already, or do you just want to start with the first one?
I did A, but I don't know if I'm doing it.
Okay.
Well, I already tried doing all of them, but I haven't put them in because I think they're wrong. Like, you gave me that A was wrong already, so.
Okay. Let's go ahead and look at A together. A looks like a little, I don't know what that looks like. Funny thing about chemistry. If you draw this on a board, in most places, they're like, that's a weird thing to draw. You draw that in a chemistry class, and they're like, oh yeah, I know what that is. So what we have to do is we have to learn how we decode this into some meaning in terms of chemical compound. And it's really because chemists love shortcuts. This is the one we're on now. Chemists love shortcuts. So in this situation, this has a bunch of shortcuts. Again, if you watch video 5, I talk about some of this. But every place where a line ends is a carbon, unless we write something else. So I'm going to go ahead and write the explicit structure associated with this. That's going to go carbon, 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 and then, oh, one more carbon there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then a weird carbon up that way. In addition to that, got to give myself a little bit more space. In addition to those carbons that were kind of hidden in this picture, any place where there is a carbon, unless we have something else written, we want it to have as many hydrogens as necessary to fill its octet. So if we have a carbon on the end like this, carbon likes to have 4 bonds. And when I say it likes, I mean based off of the electron affinity, electronegativity, and it's filling its valence shell. 4 bonds sharing 4 electrons with other compounds is how it gets to that energetic stability. But I just like to say like for shorthand. So it likes to have 4 bonds. So in order for this carbon on the end to get to its full shell, in order to get enough shared electrons to balance its electronegativity and its valence shell, 4 bonds. So we can do that to all of these that are on ends. We can just add 3 hydrogens to them. And these hydrogens, when a chemist looks at this picture, those hydrogens are just kind of understood to be there already. These carbons in the middle that only have 2 bonds to them need 1 more hydrogen each. Or sorry, 2 more hydrogens each. Right? So now if I look at this carbon, 4 bonds, this carbon, 4 bonds, This carbon, 4 bonds, this carbon, 4 bonds, this carbon, 4 bonds. And most people stop there, and they miss this middle carbon. That carbon needs one more hydrogen as well. You can see why it's nicer to write it like this instead of like this. If you're trying to make things short and you're trying to do something quick, a couple squiggles where everyone understands what you mean is great. This just takes up a lot more space and it's a little bit more clunky. It makes it harder in the next problem we're going to do with functional groups. Doing these pictures where you draw out everything explicitly makes it more difficult to see the functional groups as well. So now let's go ahead and count. 1, 2, 3, 4, 5, 6 carbons. So we'll call that C6. And then we'll count our hydrogens. 3, 6, 9, 10, 11, 12, 13, 14. So that one, A, should be C6H14. Any questions about that? Okay, now for fun, because, you know, I'm a chemist, we're going to do D. We don't have to do D, but let's go ahead and do D just for fun. Here's our structure. Go ahead, pull it up on your lab pal and start working on it. I'm going to go ahead and I don't have enough space. Like if I tried to draw this with everything explicitly, I'd run out of space. So I'm going to do this highlighting, where I'm just going to put green dots wherever there are carbons. Oh, that's not working so well. The green is becoming black. So I'll have to erase and put green dots in. That's working better. So I'm going to put green dots in wherever there are carbons. For me, that just makes it easier to count. I'm trying to make it more visually distinct. Technically, I probably could do it without doing that because I'm a chemist. But to make it more visually distinct for everybody, I'm going to put these green dots in. Also, with big structures like this, I'm very likely to lose track. And this should help us keep from losing track a little bit. So that's it for the carbons. All we have in this is carbons and hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, I messed up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. C24. Okay, that was a lot. Okay, now I was just checking the chat. Now we're going to get the hydrogens. I'm going to use the blue to kind of mark the hydrogens. And again, I'm just going to put dots because I'm trying to do this quickly. If I was just doing this in my head, I would do it in a different way, but I want to have something visually noticeable as well. So what I'm doing to put these dots on, the hydrogens, is any place where there's a carbon, I count the number of bonds, and then I put dots to get to 4. So on these two, at the ends, there's 1 bond, so I need 3 dots. This one, there's 3 bonds, so I just need 1 more dot. This one, I've got 2 bonds, so I need 2 more dots. This one, the double bond counts as 1, 2, 3 bonds, so just 1 more dot there. This one has 1, 2, 3, 4 bonds on it already, no dots. This one, 1, 2, 3, 4, no dots. This one, 1, 2, 3, 4, no dots. This one, 1, 2, 3, 1 dot. This one, 1, 2, 3, 1 dot. This one, 1, 2, 3, 4, no dots. And we just keep going through like this. This one has 1, 2, 3, dot. This one has 4, 4, 3, 3, 4, 3, 3, 4. I'm tired of saying it out loud, but I think that's it. So any place where you look at a green dot, it should have 4 things around it, adding up the number of lines and the number of dots. And this gives us a kind of visual way, because I didn't have enough space to write everything explicitly. this should give us a nice way to count everything. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. C24, H25. Oh, empirical formula. Yeah, we can look at the empirical formula as well. I want to just look something up real quick. I'm curious in terms of what we have here, C24H25. So I'm going to put that into Google. And Google does a really good job of kind of coming up with these weird structures when you Google search for them. Wow, but this one goes to Google structure. Oh, here it is. Nope, that's not it. I found an isomer of this, which is pretty interesting. 1,5-diphenylhexane 3-ylbenzene. I was just curious if something came up. The fact that nothing's coming up has me worried that I did my count wrong. So let me check something real quick. And I guess it's okay if my count's a little bit off because, you know, this one's not graded, but I want to make sure I do it right for everybody. Bond order, yes. Let's see. Oh yeah, the answer got deleted, so I don't know the right answer. Okay. Let me just double check real quick, make sure I drew the right structure. I should probably go on to actual questions instead, but chemistry. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. C24 is correct. 3, 6, 9, 12. I think we're right. I think it's just a weird structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, I think that's close enough. So we can do these relatively complicated things. I don't feel like going through and writing it out all entirely, but we could. For this one, the empirical formula and the molecular formula are the same. The empirical formula is the smallest ratio of elements in the structure. So empirical formulas are things that are actually experimentally determined from mass ratio. So instead of getting the exact number of carbons, you've got the weight of carbon relative to the weight of hydrogen. For this one, 6 and 14 have a factor of 2 in common. So that would be C3H7 would be the empirical formula. Interestingly enough, C3H7 has a whole lot of things that it's the empirical formula for. Yeah, it could be C6H14, but it could also be C9H21, right? Because the ratio, divide by 3, you get the same thing. It could be C30H70. Divide by 10, you get to the same thing. All of those, this is C3H7 is the empirical formula for all 3 of those, and for essentially trillions of other things, because you can just multiply by a constant factor. So in some experimental methods, these 3 things would all have the same ratio of carbon mass to hydrogen mass. It's kind of neat. Okay, Now, in terms of bond order, I should really double check how the other instructors are doing it, because I have to admit something. When I do bond order, I do it in terms of molecular orbital theory, which is in Chem 129 or Chem 126. I usually don't do much in terms of bond order in Chem 127 and 124, besides just counting the number of bonds something has. So if we looked at this carbon, it has a bond order of 1, 2, 3, 4, because it's got 4 bonds around it. If you look at this carbon, 1, 2, 3, 4. 4 bonds around it. The place where bond order gets a little bit more tricky is when you have things with resonance structures, when those structures can change the way that they behave, or when the structures have electrons that are more dynamic that can move around. Because essentially, whether we do it in terms of the line drawing or whether we do it in terms of the explicit drawing, whether we do it in terms of, we'll do the nitrogen compound here again, whether we're doing it for N2O2 where we've got things with lone pairs and bonds, we have to realize that all of this is a cartoon representation of a dynamic system, right? Electrons are not dots that sit on one side of the oxygen or the other. They're these dynamic, constantly moving objects that kind of build a cloud across the entire molecule. There are places where we're more likely to find them in terms of the bonds, but the electrons can be dynamic, they're moving. And that's where resonance structures come in, and this idea of, well, how do you calculate the bond order of something that has the electrons moving? And you have to take an average of bond orders, which is where you can get weird fractions and things like that. But for these things that don't have resonance structures, you're really just counting the number of bonds around each atom. Does that clear up bond order a little bit? Not all the way. Okay, let me see. Do you have a particular problem that asks about bond order that we could look at? 4C on Mastery Question 6. What's the bond order? So that example is carbonate. So that problem, carbonate, will have formal charge possible. Or sorry, formal charge. That structure will have resonance structures associated with it. That is to say, there are going to be several things with the same lowest formal charge. And for that reason, we're going to end up with an average of the structures. Did you watch, did Dr. HoursWeek4Tues video get posted? So, did you watch Dr. Scott's videos on formal charge and resonance structures? Okay. I'm not sure if he did one. Oh, there's not the bond order. Let me check something real quick. I'm trying to remember where to check it. I believe because of this particular problem, Dr. HoursWeek4Tues made a video but he just made it yesterday, so I didn't post it this weekend when I made the rest of the page. And I just want to double check that real quick. Yeah, no, I'm trying to remember if it was for this material or something else, so I'm just checking real quick. Yes, okay. So I'm adding another video up. Sorry, this is my apologies for not having this video up sooner. I'll do it right there. Oh, I can't type. So there's a new video up. My apologies for not having that up sooner. There's a video by Dr. HoursWeek4Tues that talks about how to do bond order with resonance structures. Before I do that, so if you don't mind, Ashley, I will get to that one, but I want to do the functional groups counting problem first, because that one's going to be a little bit more straightforward, and then we'll come back to that. So let's start with looking at functional groups. Okay, so moving on to talking about functional groups. This is in the molecular structures activity. Functional groups, it asks us to identify the number of functional groups in testosterone and in aspirin. And the things we have to watch out for, the thing that usually catches people off guard is they try to count things as separate functional groups. So I'm going to focus in on one on the aspirin. I should really just open this up on LabPal, but I'm going to do it this way instead. I don't draw enough organic structures in my life. So here's the structure for aspirin. Kind of crudely drawn. One of the mistakes people make is they'll count this as an alcohol and this as a ketone, when if you have those two things that close to each other, that's a carboxylic. So this is not an alcohol and a ketone. Whenever you've got oxygens that close to each other, it's actually one functional group. So this really requires us to be really comfortable and familiar with our different functional groups. This as well, this looks like, I always mess it up. This looks like an ether and a ketone, but it's actually an ester, right? So this situation again, you could look at this and say, oh, oxygen in the middle of two things, in the middle of two carbons, that's an ether. Oxygen double bond, that's a ketone. But these two oxygens that close to each other counts as one functional group, and that's going to be an ester. So looking for these things that look like they could be two separate functional groups when they're actually one functional group. The big tell for that is whenever we have things with high electronegativity close to each other, they're going to interact with each other, and so we define that as one functional group. And then we also can't forget to include the alkenes, the double bonds. Because this one, interesting. Oh no, it's up in the earlier part. So there's a part that doesn't have pictures to it as well that we have to watch out for. That says a carbon-carbon double bond is an alkene, a carbon-carbon triple bond is an alkyne. So we have to make sure we're looking for that. Those double bonds are going to be alkenes. In the print version of this, it specifically has a picture to go along with that. Okay. So, okay, that makes sense with the workshop I'm enrolled in. When you say count all of them, what do you mean? Oh, count them separately and together. No, the problem is this would never be separated. This is a carboxylic acid group. Anytime you've got an oxygen next to an alcohol like that, it's a carboxylic acid. You don't split it up at all. And it's really about how electrons get pulled around the molecule and where you're likely to have different types of reactions. So count them together. Testosterone, I'll let you do. I think that one's a little bit more straightforward. You don't have this same problem. You're going to have your alcohol, your ketone, and your alkene. The one hint I'll give, so I'll mention something that's, again, I don't do organic chemistry that much. So the thing that was hardest for me to remember was the difference between ketone and aldehyde. I don't think I got that until I was like at the end of my sophomore year taking organic chemistry when I finally learned the difference between ketone and aldehyde. So I'm going to do a little carbon chain, oxygen double bond in the middle, fill it out with hydrogens. And then for the aldehyde example, I'll do the same kind of carbon chain, except I'll put my oxygen on the end. You'll notice both of these structures are 1, 2, 3, 4, 5, 6. They're C3H6O, 1, 2, 3, 4, 5, 6, C3H6O. But this one has the double bond in the middle. K is in the middle of the alphabet. So ketones are in the middle. Aldehyde is at the end of the alphabet, beginning of the alphabet, A. And this is at one of the ends. Whether you're going this way, if you're counting this way, it's at the beginning. Also, something funny that students have trouble with, that I'll just mention really quick. A lot of people will think that these are two different structures because the oxygen double bond is in a different spot. But again, we have to remember, these are dynamic objects that can flip and rotate in space. So this structure, if I could imagine picking this structure up off the paper and flipping it around, I would just get this structure again. These are actually the same thing twice, just rotated in three-dimensional space. One of the biggest problems, this is a lot of what we were doing with the crystal structure activity last week, was how do we make these 2D, 3D representations? How do you make something that's on flat paper or on a flat board that translates to a three-dimensional object that can tumble in space? So we got to be careful about that. Okay. Now, I'll add one more thing to the list. Okay, so the last thing for us to look at so far is going to be bond order, particularly for this carbon structure like this. So the problem with this structure, and everyone in office hours said that they are doing okay with resonance structures. So the problem with this structure, which is going to have a -2 on it, is the electrons, again, are these dynamic objects. They're not just stuck in one spot. And the way that we represent the fact that the electrons are dynamic and can be moving is essentially we make a flip book, right? But we make the flip book kind of side by side. And we say, oh, it could be flipping back and forth to this as well. Or it could be flipping back and forth to this. Oh. So we end up with 3 different structures. You'll notice the 3 structures look very similar, or it could be flipping back and forth between that. And what's actually happening is this is not the same as the thing I just mentioned, where if you pick this up, you rotate it in 3-dimensional space. If I drew these and tried to tell you they are 2 separate compounds, I would be wrong. But what we're representing here is 2 resonance structures to the same compound. So what we're trying to actually show is the way that the electrons can move across the molecule. In each of these, if I'm looking at this carbon, I'm just going to count the bonds around it. And I would count 1, 2, 3, 4. Bond order is 4. In this one, bond order is 4. In this one's bond order is 4. However, I have to average that bond order over all 3 structures. So we end up with a bond order of 4/3, or 1 1/3. So we have to recognize how many resonance structures there are in the compound, how many are possible in the compound, and understand how the electrons are kind of dynamically moving in order to get to the correct bond order associated with this. And again, I apologize that I didn't post Dr. Cantu's video earlier. I'm sure he'll go through it with a little bit more detail than I just did.